Good afternoon, and welcome back to CS240, this intro to computer systems, and we're going to get started exactly where we left off. So remember, we are taking a journey through multi-programming right now, and we were talking about using multiple threads, and the last thing we did to refresh you where we're at is we ran some Python code, and we had a thread that was counting up one by one, and we had multiple threads running at the same time. And what happened was, when we actually ran these threads, we saw that if we ran 16 threads at a time, each counting to 1 million, we saw the answer was like 2 million or 3 million, an answer far less than the 16 million that we needed. And we said we needed to fix this with synchronization. So today, that's going to be what we're going to spend the entire lecture on, is how do we go about solving this problem. And there are three major techniques that we have inside of C that lets us synchronize code that's being ran by multiple threads at the same time. Because remember, you may have multiple cores, or even if you only have a single core, you have these time interrupts that are happening all the time to swap out which thread is running, even if they make no system calls at all. And the first synchronization technique is the simplest. And we call this technique a Mutex Lock. So technique number one is a Mutex Lock. And the way a Mutex lock works is it simply works like a padlock, or some other kind of lock, where it is basically either locked or unlocked. So it can only have two states. It's either locked or unlocked. It's a binary thing, and the big idea is if it is locked, no one can get the lock. And if it's unlocked, whoever got to the unlock first will get the lock and will hold on to it until it unlocks it for someone else to go in. So there are just 4 calls in C that allows us to use this mutex. So we have Pthread Mutex init. So this initializes the lock. So every time, and this is going to happen, you're generally going to do this before threading. So this is going to happen before pthread create. So you have to initialize it before the threads actually use it. So generally, one of the first things you're going to do is you're going to initialize all of the individual threads, or sorry, all of the individual locks that you might need to use. And then you have 2 calls to actually use the lock. You have Pthread Mutex Lock, and this takes in a pointer to the lock. So you've initialized the Pthread Mutex type. You're going to send that mutex into the Pthread Mutex lock. And this line of code is going to do one of 2 different things depending on the state of your mutex lock. If your lock is currently locked, if your lock is currently unlocked, it's going to change the lock to a lock state and allow your program to continue. If the mutex is currently in a lock state, that somebody else has already locked it, then Pthread Mutex Lock is going to block until it has received the lock. So it's going to change the thread state from being able to be running to being in a block state, and it won't continue running. Your program will be stuck at that line of code, stuck at Pthread Mutex Lock, until someone else unlocks the lock so you can get access to the lock itself. So it's going to block the current execution of your code. Then to actually unlock the lock, you simply use Pthread Mutex Lock, and then you can destroy the lock once you're done with it to free up all the memory. Yeah, Jake. Yep, so if you have 2 different threads running at the same time, and if they both are getting to the lock at the exact same moment, one of them is going to be able to get the lock and continue, the other one's going to be blocked. So you won't ever have the same thread getting to lock twice. Well, if you ever have the same thread getting to the same lock twice without unlocking it, it's going to deadlock on itself. So this is generally only should happen when you have 2 different threads. So you have 2 threads each competing for the same resource. Yeah, Matt. Yeah. So will the second, that's a great question. Will the second one be queued up to get the lock? So the POSIX library, if you read the documentation for the Mutex lock, it doesn't guarantee any order. So it is waiting for the lock. I wouldn't use the word queue because queue implies an order. Does that make sense? So if you basically have 10 threads that are waiting for that lock, you don't know which one of these 10 threads are going to get the lock. It's not guaranteed to be the first one to have called Mutex Lock. It may be on certain systems, because like Linux may have implemented a queue to do that, but it's not guaranteed to be a queue. So on a Mac, it may work as a queue. On Linux, it may not. You'd have to look at how they choose to implement it. Great question. Any others? So we've got this lock. We've got this object that we can either lock or unlock. And I think the best way to look at this is to look at the count program that we just saw. So the reason we use locks is locks allow us to protect critical sections. So we have this idea that this is our critical section. So remember, the critical section accesses global variables that are shared between multiple threads. So here, CT is a global variable that's shared between all of the threads that are counting up. So because CT is this global variable, we have to protect all of the code that accesses CT. Luckily for us, it's only a single line of code here. So right before we're going to access CT, we're going to call Pthread Mutex Lock so that we know that we're the only person of all 16 threads that are running that's allowed to touch CT while we have the lock. And then we're going to access our critical section, run through the code that can only be accessed by a single thread at a time because it's using a shared resource. And then as soon as we finish running our critical section, we're going to give the lock back so someone else can get a chance. So all I've added here is I've added a Mutex Lock, and this has been initted in main. So we have this lock structure that we've initted in main. Now we call Pthread Mutex Lock right before a critical section, Pthread Mutex Lock unlock after our critical section, and that's it. So we have otherwise exactly the same program, except for we've added a Mutex Lock and protected our critical section. So what do we think is going to happen now? If I run the program 1,000,016, you have 16 threads counting up to 1 million, given that I've promised that I've protected our shared resource, what should the answer be? Yeah, room? 16 million. Should be 16 million. Let's see if that actually happens. So for every single lecture, I'm always posting the code in the lecture Git. So in fact, I just Git pulled my own code down to this computer since I dev on a different computer than this one. And so if I go into here, I'm going to go into the lecture 9 directory and see count using locks. So you have access to this code as well, and you'll see I've done a Pthread Mutex init down in main. And I need to go ahead and compile this code, so cd09 gcc count using locks minus l pthread. All right, it compiled, perfect. And then if I run /a.out, I need to say count to 1 million with 16 threads. So I'm doing this, and what do I get? 16 million. But let me actually run to 10 million. So if I have 10 million with 16 threads, I do this, but it's taking a little while. So I get the right answer, but I might have to sit here for a while. Okay, so that took probably like 20 seconds. And if I go run .08 count of 10 million, 16, it runs much, much quicker. So what happened to the performance of this program once we introduced locks? Was it noticeably slower? Yeah, way slower, like a factor of 10 slower. So what we saw was we got the correct answer, but the program was way slower. Why would it be slower? Why would adding a few locks slow this thing down? Yeah.
Because you're essentially using single threading when you introduce a Mutex Lock, because every single thread has to be able to count once at a time.
Yeah, I'm sort of introducing single threading. I'm not quite going as crazy as single threading because I do have 16 threads competing for the lock. Jake, did you want to add something? Yeah, so I am kind of taking out the parallelism of the counting, right? So I do have 16 threads running at the same time. They all are looping together, but now they have to increment the counter one by one. They can't both be adding at the same time. So I can really only use one core to do the addition. And so that's one reason. So one reason is I'm only accessing CT by a single thread at a time instead of using all 4 of my cores on this machine. The second thing is there is a lot of overhead in actually locking a lock. Locks are incredibly expensive. So what a lock has to do is it has to say, hey, everyone else on the system, I need exclusive access. So locks are not cheap. And if you're calling this lock 160 million times, that's a lot of calls to say, hey, everyone in the system, make sure that you're not accessing this. I need exclusive rights to this. That's really, really expensive. So we still do get parallelism. We still get a bunch of threads running, but we have our critical section only running by one thread. So as a good design principle, we want to use locks only when absolutely necessary, because they give us the correct answer. They fix our synchronization problem. But we want to use them sparingly if possible, because locks are slow. Yeah, Aaron. Oh, interesting. So what about 110 million, or I'll do 100 million. So 100 million, I'm going to do time of 100 million. So how long did it take us to count 100 million with no locks? And that was, the total time was 0.27. And now if I run /a.out, what is the overhead of just a single thread? I now have 1.8 seconds. So I go from 0.27 to 1.8. So what is that, a factor of like 7? So yeah, that's raw. That's a great example. That's like the raw overhead. That we don't have any threads competing for it. It's single thread in both cases. But just by adding that Mutex Lock call, we added a factor of 7 overhead. Cool. Anything else? So Mutex locks, the key takeaway is anytime you have a region of code that is accessing a shared variable, Mutex locks are a great resource to ensure that only one thread is accessing that shared variable. So Mutex locks aren't my favorite form of synchronization, though. There is a really, really cool paradigm that really, if you understand how to use our second synchronization technique, it unlocks so much power that you can use inside of your programming. So Mutex locks are really great for that one case where you want to protect a single variable. But our second technique is called a conditional variable. So synchronization technique 2 is our conditional variable. So these are often abbreviated as simply CV. So you'll often see this if you look at kind of system literature, people will talk about your CV. This is not your resume. This is a conditional variable. And a conditional variable, the purpose of the conditional variable is the conditional variable allows for verification of state within a critical section. So what this means is a Mutex lock only guarantees that the code in between the lock and the unlock is only going to be ran at one thread at a time. But what if we only want to continue running if some condition is true? What if we only want to be able to continue into our code if our queue is empty? Or what if we want to block if the queue is full so that we can empty out the queue before we add more data? What if there's some state about how our program's running that we want to decide whether or not we enter into a critical section? And this is super, super important for so many applications. So if you think about how web servers work, how databases work, all of them rely on conditional variables to verify some state before it enters into a critical section. So these are one of the hardest ones to really wrap your heads around. This is a difficult concept because of how it interacts with the rest of the world. So there are actually there's five common calls you're going to make as part of the API for conditional variables. The first one and last one are pthread condition init and pthread condition destroy. These are pretty straightforward. The ones that actually do all the work are the middle three. So pthread condition wait is probably one of the most complicated synchronization calls because it does two things related to synchronization. The first action it's going to do is it is going to check, or it is going to unlock the mutex until condition is unblocked. So you actually pass in a mutex, you pass in a mutex T that needs to be locked. So this mutex, you need to have locked it. So it's going to unlock the mutex you pass into condition wait. So it unlocks the mutex that you pass into it, and it blocks until your condition is unblocked. So it's going to give up the mutex. So it's going to say, I'm going to give up my lock, and I'm going to block until somebody tells me to move, until someone tells me to wake up. So I'm going to give up my lock, and I'm going to wait until somebody tells me to wake up, and then I'm going to get the lock back before I return. So it only unlocks the mutex until the condition is unblocked. As soon as the condition is unblocked, it's going to get back the lock. So even though internally it's giving up the lock, you're going to keep this code inside of a mutex lock block. And the way we wake up a thing that's stuck inside a condition wait is we either signal it. So the signal says that it unlocks at least one thread, is what the documentation says. So what my experience is, signal usually unblocks one thing. So if you just want one thing randomly to wake up, signal works great. I guess it's not guaranteed to just be one. I guess in some systems it might be more than one. I've always seen it be exactly one. So it's going to wake up something that is stuck in a condition wait. Or if you want to wake up everything, you can just do condition broadcast. So in general, if you're not sure what to do, you can do a condition broadcast. The condition broadcast will always work. It will just be less performant. So this is a lot of abstract stuff. So I think it's best to kind of look at code. So I want to look at a classic problem, which is called the producer's consumers problem. So here is a snippet of code from producerconsumer.c that you also have in your handout. And I want to take a look at a few different things. So first I want to talk 225 with you. I see that I have on line 11 an int things that has a things max, and I'm adding things at things CT and incrementing CT on lines 24 and 26. So I've got this array that is of some length, maybe like 10 things can go inside of it. And I'm adding things to the array, and I'm also taking off from the end of the array. So I'm basically incrementing my count until as I add something to 0, I add it to 0, increment my count, add to 1, then I add it to index 1, then I add it to index 2, index 3, and as I remove things from things, I then take it from 3, then take it from 2, take it from 1. If I add to 2, then I go to 2, 3, 4, 3, 2, so forth. What data structure did I just build? I'm always adding to the end of the array, and I'm always taking off from the end of the array. Stack, yes. So I'm building a stack here, and my stack is a fixed size. So I'm not using a linked list, I'm using an array, so I have a capacity that it can't go bigger than things max. So this is a capacity-bound stack. And in my capacity-bound stack, I have 2 threads. One thread is going to be producing things, that's going to be adding things to my stack. The other thing is going to be consuming things and removing things from my stack. And what I have here is if I produce a thing, I'm going to go to whatever my current count is, add just a random number to it to produce a thing, print out that I produced a thing, and then increment my counter. And because this is a global variable, things is global, I have all of this inside of a Pthread Mutex Lock unlock statement. So this whole thing is now my critical section. Whole block of code. And the reason it's a critical section, I'm accessing my global variables. I'm accessing like things count. I'm accessing things count here, things count here, things here, things count here. I'm accessing all of these bits of all of these global variables all over my critical section. So when can I not, so because I have a capacity bound stack, when should I stop producing? Yeah, when my stack is full. So what I'm going to do, and here's where conditional variables are fantastic, is what I'm going to do is I'm going to check if my stack is full. And I'm going to do that by saying while the things count is greater than or equal to things max, hopefully it'll never be greater than. I could have probably had an equality statement, but basically this says, while my stack is full, then I want to wait until that condition has changed or potentially changed. So every time you use a conditional variable, every use of a CV should always be in a while loop. And the while loop should always be checking the condition that you don't want to continue on. So what I'm saying is I do not want to continue if my stack is full. And if my stack is full, then I am going to say, I'm going to condition wait, and I'm going to wait until somebody tells me that the state of the stack has changed. So then our responsibility as programmers is every time we change the state of the stack, we need to signal that conditional. Because remember, it gets stuck in that line of code, in pthread condition wait, until somebody signals it. So what we see is we're going to signal it at the end of, as soon as we've modified the stack itself. So I'm saying, hey, the stack's modified. The list of things may be different now. So I'm going to say, wake up and check your conditional again. And here, what we have here is this is just a producer. We also have an identical set of code for the consumer that consumes from the stack. And it's going to make sure, so if we have the consumer code, what should the while statement in the consumer? Where should the consumer never continue? Consumer should never actually run its code if the stack is empty, yeah. So we're going to be checking, while the stack is empty, we want to wait for the stack's condition to change. And then it's going to consume the object on the stack, and then it is going to notify that the condition of the stack has changed. So this is a little complicated because we have this idea of a conditional variable that we're going to call out to based on some condition not being met. And then whenever we change that condition, so that condition might be met later, we have to broadcast our signal to the conditional variable. So, and just to show you the code here, I'm going to go ahead and open up producer consumer, and we see that the consumer does exactly that. That while the things count is equal to 0, then we're going to call the condition wait. So we're going to say we should not continue with our execution of this code until we know that the condition is no longer 0. And then once the condition's not 0, we know we can consume a thing, and we go ahead and consume the thing, print out that we consume the thing, and because the state of the stack has changed, we're going to broadcast on our conditional variable. And say, hey, everyone who's waiting on something, wake up and see if your condition's met now. So does that make sense on what the purpose of the conditional variable is? The two big takeaways is conditional variables always need to be in a while loop that's constantly checking its condition. So that when it gets woken up, it doesn't know if the condition's actually accurate at that point. It just knows that the state of the resource has changed. It needs to re-verify whether or not that state has changed in a way that it can now proceed. The state may have changed in any number of ways. The conditional variable just says the state has changed. And the other thing is conditional waits have to be inside of a mutex lock. They have to be used inside a critical section. So what they do is they give up that access to the critical section while it's blocked. But notice I have a Pthread Mutex wait, or sorry, Pthread Mutex lock and a Pthread Mutex unlock around the Pthread condition wait. So all of this happens within a critical section. So this is a combination of mutexes and conditional variables. Any questions? Yeah, Matt.
Within that while one loop, like the while true loop,
yeah.
you have the lock and unlock. Does that mean it's iterating, it's doing multiple iterations of that while true loop, and every time it's locking and it's unlocking and it's locking and it's unlocking?
Yeah, so every time, so we wouldn't want to lock outside of the loop, because if we lock outside of the loop, then we're just basically going to continually have the critical section. No one else is going to get it run. So basically what I'm doing here is I'm grabbing the lock, doing what I need to do inside my critical section, giving up the lock for someone else to run. Yeah, you never want to lock the entire while true loop. Yeah, Aaron.
Is there a risk that you have multiple threads being on conditions and then get locked off them and they from like multiple thread sessions?
So is there a problem that, what happens when we broadcast and there's now 5 threads all waiting on conditional locks? They all wake up at the same time, right? Because conditional wait requires the mutex lock to be given back to the thread. If you have 5 threads that are queued up to now wake up, 5 threads that have moved to the ready state, only one of them is going to get a run at a time. Because you have to, you're guaranteed to get the lock back before you exit pthread condition wait. So you're sort of giving up the lock for just, you're giving up the lock while you're waiting, but before you return from that call, you get the lock back. So you're guaranteed that only one thread is inside this critical section, even if you've woken up 10 of them. Yeah? How is the one decided? Yeah, the operating system probably has some way it decides. It doesn't guarantee any order, though. So let's see if this actually works. So I'm going to go ahead and gcc producer consumer.c minus lp thread and run ./a.out. And what I see is I am producing and consuming, and I see that number gets up to 9 and goes all the way down to 0. And I occasionally see 1s, 2s, and 3s in the middle. And forever I'm producing and consuming. But notice I never get up to 10. I never go down to -1. And as this runs forever and ever and ever and ever inside my while loop, I am protecting against buffer overflow and buffer underrun. never segfaulting, never accessing a -1, never accessing a 10. So this is very similar to what you're going to be doing in MP4 that we'll talk about in a second. Yeah? So is the overhead more than a mutex lock? By definition, yes, because as part of the condition weight, you actually have a mutex lock inside of it, right? So this is an abstraction built on top of locks to allow us to check state. But this would be basically impossible to do with just locks. So if you just had a lock and you had to wait for somebody else to produce something, the best you could do is say, I'm going to take a lock, I'm going to see if the queue is empty. If the queue is empty, so that I can't consume something, then I'm going to give up the lock and just like sleep or something for someone else to do some work. So you'd have to constantly be checking your condition in like a while loop to see if you can actually produce something or consume something. So what this does, it allows us to move to the block state and wait for us to be signaled that the condition has changed, rather than having to constantly check if the condition has changed. All right, and this is still running. There we go. So we see that exactly what so here, at the very end, I was just sort of producing consumer. I was kind of up there. We finally got down to, I saw an 8 for a second. Oh, there. Somehow we went from 9, we consumed all the way down to 1, then started producing again. Back up to 9. So we see that we produce, consume, it's all working as expected. Any questions on this? So you're going to get a lot more practice using this on MP4. So MP4, what you're going to get to do is you're going to manage a resource wallet. So a resource wallet is going to have a number of resources. So the resource example that I made for you in MP4 was I want you to generate a degree. So to generate a degree, I might want to generate smaller elements of something. And this was actually inspired by just randomly, I was like, resources are something that you have to have enough of to buy something else. So have any of you actually ever played Cookie Clicker? Do any of you know what Cookie Clicker is? Okay, has anyone never heard of Cookie Clicker? Okay, a few people have never heard of Cookie Clicker. Few people. So Cookie Clicker is like the worst thing on the internet. So Cookie Clicker is this like dumb game that came out, I don't know, 10 years ago, 15 years ago? A long time ago. And basically the premise of this entire thing is that you click a cookie, and as I click this cookie, I eventually have enough things to actually buy something with my cookies. And here I can like buy a pointer thingy. And this pointer thingy then actually produces a 1/10 of a cookie every single second for me. So I have something that's now generating cookies for me, so I've kind of like outsourced my clicking. And then you can obviously get lots more cookies and keep clicking and eventually get bigger and bigger things. So if I click 100 times with the help of a little auto clicker, I eventually get to buying a grandma who will bake cookies for me. So here, I need 100 cookies to buy a grandma who will bake cookies and then increases my cookies per second that's auto-generating for me from what was at 0.1 to now 1.1. And I can watch this number basically go up. And this game, literally, some people have played it for 10 years straight. It's a game you can never beat and is all about just watching numbers go up. So this kind of inspired this idea that one thing that is happening behind the scenes is you cannot actually buy a second grandma until you have at least 115 cookies. So if you had something that was buying a grandma, you could basically constantly be in a while loop that says, do I have 115 cookies? If not, try again. If not, try again. If not, try again. If not, try again. Or I could have a conditional variable that says, when my cookies have changed, let me know, and I'll check whether or not I can buy a grandma. So you're going to be doing that for MP4. There's no automation of resources per se, except for to earn a degree, we're going to have some threads that are generating science for you. Some threads that are generating textbooks for you. Some threads that are generating, I think I've got 4-leaf clovers in there and other clovers in there. I've got a bunch of random emojis that we're generating. So you've got like 15 different threads all generating resources at the same time. And to actually create a science diploma, you have to consume 50 books and 20 beakers. So what you need to do is you need to create a wallet that will be able to store all of these resources. And you're going to be programming a wallet get function where if I want to take from the wallet a negative number of resources, you have to block that wallet until that number of resources is available. So if I need to produce a cursor, and that cursor takes 18 cookies, then in MP4, I am going to basically have, I'm going to call wallet get, and I'm going to say I need negative 18 cookies. And this wallet get function must block until your wallet has 18 cookies in it. You can never go in debt in your wallet. And now you know how to block until you have 18 cookies. But there's also going to be other threads that are going to call wallet get of 1 or something to add a cookie. So obviously, you can't just lock on cookies when you have negative 18 because a different thread needs to come in and actually add a cookie for you. So you could constantly check inside a while loop to see, do I have at least 18 cookies? Can I satisfy this request and not go into debt? Or to get full points on the MP, you're going to get to use mutex and conditional variables to make sure that you're not busy waiting, that you're just blocking until someone generates a cookie. Only once someone generates a cookie, do you then check again whether or not you have the 18 cookies. So most all of MP5 is dealing with now programs that have 20 threads running at the same time, all adding and subtracting resources, and your job is to make sure that we can access that one shared wallet that's shared between all of the threads safely, and doing so efficiently by only checking by blocking if I can't satisfy the request, and only checking whether or not the request is satisfied when that resource is changed in the wallet. And that's all for MP4. I've set up a few different fun examples. I have one that you're earning a degree, and that's a complicated example. I also have a simpler example to help you debug called Simple Hedgehog, where the only 2 generators is one generates hedgehog food, a cute little worm emoji. And if you consume, I think, 3 worms, 5 worms, I forget exactly how many worms I consumed. But I consumed like 5 worms, negative 5 worms, to create a new hedgehog. So you've got this thing that's generating hedgehog food every single second. And once you have 5 hedgehog food, a different thread is going to be able to convert those 5 worms or 5 hedgehog food into a hedgehog. And that's a really simple test case that I have for you that lets you debug your program with a really simple 2-thread environment instead of the crazy 20-thread environment with the generating degree. So this will let you dive into a real-life example, and there's tons of examples where you need the resources. When you need a resource that can't go negative. So you can think of like available memory inside of a system is another resource. And if you want to generate your own cute little puzzle, feel free. Like if you want to generate your own story, like I have the story of how you earn a degree. I have the story of hedgehogs. You can feel free to share your own test cases on Discord or whatever you want. So, but the key thing that you're building is this wallet that you're protecting against everything else. Any questions on MP4? So that write-up and description will be out sometime tonight, and then due Friday, a week from now, or a week from tomorrow. And as with our new policy, you have one grace period for the entire semester. So if you need an extra 3 days on any MP, just let me know, and I will regrade your MP on the Monday after the MP is due if you want to use your grace period. So if you need extra time for MP3, you need to let me know that you want to use your grace period. You only have one all semester long, or if you need it for MP4, you can use it on MP4. But once you've used it up, you've used it up. Yeah. Yeah. Yeah, so your grades on GitHub, as long as you don't modify the test cases, those should be the correct grades. I will get them moved over to Canvas soon. So you should already know what they are because of the GitHub test cases. But I will get them moved to Canvas just so you have it all in one place. Thanks for letting me know. Yeah. How many MPs? There are a total of, there was going to be 10, but because we extended MP3 to be 2 weeks, there's now just going to be 9 different MPs. Yeah. Yes, so MP4, and so the MP that's coming out today, and the MP that's coming out next week, MP5, are both in C. MP 6, 7, 8, and 9 are all in Python, and your final project's going to be in Python. Yep. Any other questions? Actually, Python's an interesting question, because I've done it in Python. The programming language doesn't really matter too much. We actually could do it in Python or in Node.js, like JavaScript and TypeScript. Is there, do you guys, who is team, so if you're team Python versus team JavaScript, who is team Python? And who's team JavaScript? Oof, Jake, you and I. Okay, I guess we're gonna do it in Python. That's easy. Okay. Any other questions on MPs or logistics? Yeah, Jake. Yes, we are using Flask. Yep. If you don't know what Flask is, it's a HTTP library for web services in Python. It's going to be the main library we use to build our web services. Any others? Okay, so we've talked about 2 techniques of synchronization. So if I flip over the page, I get to the 3rd technique of synchronization. And this 3rd technique of synchronization is called a semaphore. So a semaphore is basically it's called a counting mutex. So it's a mutex that instead of being either locked or unlocked, it has a variable that is a counter inside of it. And essentially this count, when it's at 0, no one else may enter. If it's greater than 0, we decrement it and enter. So we basically have a mutex that just simply has a count inside of it. And the count can start at whatever value we set up it to start at syminit. And then the API for it basically syminit. You create a new semaphore with a specified value or count. So you can start at 0, you can start at 10, you can start at whatever value you want. And symwait, if the value is greater than 0, decrement the value and continue, otherwise blocks until the value is non-zero. So the value of the semaphore never goes below 0. but you're going to block if the value is at 0, and you're going to wait for someone to increment it above 0 before you continue. And sympost increases the value of the counter by 1. So I have a hot take about semaphores. Semaphores, I consider kind of the trash synchronization technique. So I pretty much will never use semaphores anymore. They are incredibly hard to debug because you can't really, there are calls to get at the counter, but it's really hard to inspect the value of the counter. And because you have state now inside of your synchronization technique, that state gets really, really, really hard to manage. Because you've got to figure out, okay, what is the value of count actually mimicking? So is the value of the semaphore mimicking the number of empty spaces in the queue in our stack? And if so, every time we change our stack number of empty spaces, we got to make sure that we increase or decrease the semaphore correctly. You're basically mirroring the state of some object within your code. I think it's much more clear if you just have a while loop that actually checks the condition itself. This, if I'm looking at your code and I see this while loop with a condition wait, I know exactly what you're checking. I know the exact state it corresponds to. If I have this state encoded in a semaphore, I have no idea what this state's mimicking unless I have comments. I find semaphores incredibly hard to debug, incredibly prone to having just weird logic errors. I have only seen semaphores cause more problems than they're worth. But they exist. They're a thing. People use them. Some people love them. They're kind of they sort of sit between a mutex. So mutex is basically only on or off. A condition variable can literally do everything you want. Conditional variable, you just signal it, and then you can check whatever state you want. So that check can be as complicated or as simple as you want. In between them is, if you just want one integer that you want to keep track of, the semaphore can keep track of one integer for you. But I think you're going to have more readable code and a better understanding of what your code's doing if you just use conditional variables. Yeah?
Could you implement a semaphore with conditional variables?
Yeah. Your condition would just basically, the thing you're checking is whether or not you'd say wall value was equal to 0, condition wait. Because basically the thing that you don't want to proceed on is you don't want to proceed while the value is equal to 0. That would be a conditional variable, a semaphore implemented as a conditional variable. So that is synchronization. We've got 3 different techniques to solve synchronization problems. So now we can have multiple threads running at the same time, and we have strategies that we can use to make sure that we can synchronize the multiple threads through either a mutex or a conditional variable, or if you really want to torture yourself, you can use a semaphore. And the reason we care about these things is critical sections are going to happen a lot in code. We're going to increasingly see more and more critical sections as we go further and further into this course. There's going to be a lot of shared resource we're accessing and a lot of resource that we only want one thread to access. So critical sections allow only one process to access a resource at a time. But if we have these things locks, what can happen if we're trying to manage access to a critical section? So what's the worst? So we talk about all these things, locking, unlocking. I'm waiting on this thing. I'm going to signal this thing. What's the worst case situation? Where does this go really wrong? What if everyone, Yeah, that is the nightmare. What happens if everyone's just locking, waiting for someone else to do something? So critical sections, what if everyone is waiting for someone else? So I feel like this is like the nightmare situation where like you're at a four-way stop sign and all four of you pull up to a stop sign at exactly the same time. And it's like, who gets to go first? You're all waiting for someone else to go first. And if you're always waiting for someone else to go first and nobody takes any initiative, we call this condition deadlock. So I want to actually introduce a second classical problem. You saw about the producer-consumer problem, this idea that some things are producing, some things are consuming. I want to talk about probably the most classic problem in all of computer science, and that is the dining philosophers problem. And the dining philosophers problem is a thought experiment that involves synchronization. So it's set up that we have n philosophers sitting around the table. I'm going to choose n equals 5 for all my examples. So we have n philosophers sitting around the table. And the philosophers can either, and maybe these are philosophy students on South Campus, and all the philosophy students do is they either think or they eat. That's all they do. They don't have homework. They just, A's everywhere, right? So there's a few CS philosophy, I'm sorry. They're basically these philosophers, they either think or they eat. And to eat, they are philosophers and they're using chopsticks. So this philosopher, I'll call her P0, philosopher 0. To eat, she would need to pick up her left chopstick. I'm going to call her left chopstick C0, and her right chopstick C1. And once she has both C0 and C1, she can then eat her food, finish eating, and put her chopsticks down to begin thinking again. And then philosopher 1 may want to eat, picks up chopstick 1, picks up chopstick 2, picks up the left chopstick and the right chopstick, can eat, and then continue thinking. Same thing happens with philosopher 2, picks up chopstick 2, picks up chopstick 3, philosopher 3 picks up chopstick 3 and chopstick 4, and philosopher 4 picks up chopstick 4 and chopstick 0. So all these philosophers are going to alternate between thinking and eating, and thinking and eating, and thinking and eating. And that's all they're doing for their entire existence of philosophy. So what happens as this runs for a very, very, very long time? Yeah, Aaron? So yeah, that's a good question. What happens if there's not? I'm going to say that we are always going to pick up left, then pick up right, and then eat. Then 4, put back. So that's my series. So I'm always going to grab my left chopstick. I'm going to hold on to it until I can get my right chopstick. Then once I get my left and my right chopstick, I'm going to then eat, then put them back. So all the philosophers agreed to follow this order. So I'm always going to pick up the left, then my right, then eat. Yeah, Aaron? Oh, interesting. So Aaron said, what if every single philosopher picked up her left chopstick? So philosopher 0 picked up chopstick 0. Philosopher 1 picked up chopstick 1. Philosopher 2 picked up chopstick 2. Philosopher 3 picked up chopstick 3. And philosopher 4 picked up chopstick 4. Okay, so we've got all of these. So can any philosopher right now pick up their right chopstick? No. So they're all waiting for somebody else to finish eating so they can grab their chopstick. Ooh, this looks like deadlock. So I have all of this programmed up. So basically, I'm doing the exact code right here. So I didn't print this one out because this one's a huge, long chunk of code. Because it's mostly print statements, but essentially all I'm doing is exactly what I wrote here. I have a Pthread Mutex Lock that locks on their left chopstick. So I'm locking the left chopstick ID. Then I'm locking the right chopstick ID. And then I'm going ahead and printing out I'm eating. And then I return both my chopsticks. I return the right one and return the left one. So that's all my code's doing, is essentially going through and saying I'm thinking, picking my left chopstick, picking my right chopstick, eating, then giving back my left chopstick, right chopstick, and giving back my left chopstick. So this is the pseudocode basically to what I've done. And if I go ahead and compile this, this is called in directory 9, this is dining philosophers. I can say gcc diningphilosophers.c minus lpthread, and then run a.out. And I can see I ran for quite a while. Like my philosophers actually did a lot of work and did quite a bit of eating. But let's see exactly the case that we figured out. So philosopher 2 grabbed chopstick 2 as the very last thing that happened. Then if I scroll up a little bit, chopstick 3, then philosopher 2 is reaching for the right chopstick. So philosopher 2 has their left chopstick. Philosopher 3 has the left chopstick. Philosopher 4 has a left chopstick. Philosopher 0 has a left chopstick. And I think all we're missing is 3 needs a left chopstick. Yeah, and philosopher 3 is reaching for the left chopstick. So that situation that Aaron identified is the exact situation we see that result in this program where we have 5 threads in a while one loop. All 5 threads are trying to have these philosophers eating, and our program's completely stuck. They ran for a while, but now are completely stuck because they've all grabbed their left chopstick. They're all waiting to grab their right chopstick. None of them can actually do it. So this is the classic example of what we call deadlock. So we actually formally define deadlock as being that, so deadlock is the condition that all threads are waiting on another thread or itself so that no progress is being made. So deadlock is a situation where all threads are waiting on another thread or itself such that no progress is being made. So we saw in the dining philosopher problem, this happens when we have everyone reaching for their left chopstick all at once, and nobody is able to ever grab, or everyone has their left chopstick, and they're all waiting to grab their right chopstick. So what's beautiful about deadlock is there's actually 4 conditions that have to be present for deadlock to occur. So we can analyze any program, and we can analyze whether or not deadlock's going to occur by looking at if all 4 of these conditions are present. So what I'm going to do on this back sheet of the paper is I'm going to first list out the 4 conditions. Then we're going to go back and see how we can actually remove any one of the conditions to make the dining philosophers problem not deadlock. So these are necessary conditions. So because they are necessary conditions, that's a mathematical word that you have to have all of them. All 4 must be present. These are sometimes called the Hoffman conditions. And we have 4 of them. So the first condition is mutual exclusion. So we have to have resources. So this is the idea that each resource can only be held by one user. So once I've picked up the chopstick, no one else can pick up my chopstick. This is the idea of mutual exclusion. So the dying philosopher problem, each chopstick can only be used by one philosopher at a time. The second condition of deadlock is we have to have circular weight. So if we can say a graph of all weight edges must contain a cycle. So if we put an arrow for every single resource it's being weighted on and who it's weighting from, you're going to see that that's going to form a cycle if we make a graph out of that resource allocation. So we have to have a graph that the weight for graph results in a cycle. Third necessary condition is it has to be hold and weight. So the idea of hold and weight is that we must keep the resource once we acquire it. So once we grab the chopstick, we hold on to that chopstick until we are done with the task. Until we have finished eating, we hold on to that chopstick. If we ever put the chopstick back down and allow someone else to pick up that chopstick, we're going to break the cycle in the graph. We're no longer going to have a deadlock. So we have to have mutual exclusion, we have to have circular weight, we have to have hold and weight, and we have to have something that's kind of related to all the three things, but we have to have no preemption. So this is the idea that no one can take a resource from us. No one can take a resource from us. So these are the four conditions that we absolutely have to have every time we have deadlock. So if we think about these four conditions, what if we remove mutual exclusion? So in the dying philosopher problem, how do we get rid of mutual exclusion? What is one way we can get rid of the mutual exclusion condition? How do we modify that problem? Yeah. Yeah, so every single chopstick is now actually an infinite stack of chopsticks. So you don't actually just own one chopstick. Yeah, so this is like disposable COVID masks. They seem to be infinite, right? So they're essentially not a limited resource. You have a potentially limitless number of them. Multiple people can grab from that stack of chopsticks. So yeah, one way to break deadlock, so to avoid it, have a stack of chopsticks. And because they are four necessary conditions for deadlock, that means if we remove just one of the conditions, we no longer have deadlock. So when we think about designing an algorithm, if our algorithm does not have mutual exclusion, if our algorithm doesn't have a single resource that can only be grabbed by one party, then we avoid deadlock. Yeah, Jake? Would this particular example work with two chopsticks? Yes. Though if you have two chopsticks, I'm going to argue that you've actually more avoided a different condition of deadlock as much as avoiding mutual exclusion. Because you still have mutual exclusion, what you've just done is you've added extra resource so you don't get a cycle. So I'd say that's more avoiding the cycle than it is this idea of mutual exclusion. But yeah, both of those definitely solve deadlock. So Jake kind of argued this one, so circular weight. So all we need to do to avoid circular weight, we need to just break the cycle. So I think one way to break the cycle is what Jake just said. We can add an extra chopstick. So as soon as you have a chopstick, so that if we add an extra chopstick here, so that one table setting has 2 chopsticks between the 2 philosophers, that alone is going to prevent a cycle from forming. But let's say these chopsticks are made of like platinum and gold. They're $1 million chopsticks. I don't want to add another chopstick. I don't got that budget. Is there a way to avoid a cycle without, yeah, Lloyd? You can move all the chopsticks to one place, but I think, how does that not prevent all 5 of us from walking up to that one place and grabbing the first one at the same time? Yeah. Could you do grab 2 or grab none? I mean, yeah, that would. Yeah, so you could do sort of, I guess, that, I'm going to actually say that if you're grabbing both of them, and only basically doing that if you can get both of them, that's actually going to be avoiding preemption. Because essentially what you're saying is I'm going to grab the left one, and if I can't grab the right one, I'm going to put my left one back, is essentially what I implement the algorithm as. Yeah, so that's really avoiding preemption. So that's a 3rd condition. Or sorry, 4th condition. Or maybe 3rd, it might be hold and wait, I don't know. All of these kind of merge together a little bit. Yeah. So some people could grab the left one, some people could grab the right one, but if we do that randomly, isn't there a chance that we all grab the left one once? Or are you saying not randomly? Oh, okay, interesting. So we can have some people grab the left one first, and some people grab the right one. So now whoever gets this chopstick first is going to be able to grab maybe this second chopstick. So if one person grabs the other way. So I'm going to clean that answer up. That answer totally works. But I'm going to clean it up to be a little bit nicer. So if you always, so we labeled all of these chopsticks as, we have P0 grabbing chopstick 0, chopstick 1, P1, P2, P3, P4, C2, C3, C4. What if we always grabbed the lowest number resource? So what that means is that philosopher 0 is going to grab chopstick 0. It's going to grab its left first. But philosopher 4 is going to grab its right first. So I've essentially done what you've done, right? I've swapped the order one of them is grabbing it. So you actually avoid a cycle on a graph if you create a total ordering of all resources. And use the ordering. So if you create a total ordering that everyone agrees on, and you always grab based on the total ordering of all the resources. So if you have 0, 1, 2, 3, 4, so it has to be a total ordering, has to have all the resources have to be less than or greater than another resource. It's got to be a global agreed upon order. But if everyone always goes for resource 0 first, then if somebody needs both 0 and 1, they're always going to be grabbing 0 first. If someone needs 0 and 4, they have to grab 0 first before they can grab 1. So if you guarantee a total ordering, what you actually end up with is a tree structure. And you know from 225 that if you have a tree, does a tree ever contain a cycle? No. So yeah, basically by having a total order, we've transformed this graph into a tree structure. And by having a tree structure, we guarantee there's no cycles. So that's kind of the mathematically cleaner way of kind of thinking about the breaking up a cycle. So third thing, hold and wait. Remind me, what did you propose for hold and wait? Yeah, I'm actually, so I was thinking no preemption, hold and wait. I actually think it's best as hold and wait. Yeah. So the idea is that if, so you avoid by saying if you cannot acquire both, put everything down. But, so this is going to avoid deadlock. This actually has another problem that happens. What might happen if I give up everything I'm taking? So could there be a universe where Kevin and I are both trying to eat, and I try and grab this chopstick, I grab it, I see I can't grab his other chopstick, I put it down. Could I just keep doing this forever? Am I actually ever advancing into my critical section? No. So this is vulnerable to something called live lock, where I think I'm actually doing work. I am literally picking up and putting down my chopstick. So this does cause live lock. It's the idea that I'm making progress, but I'm not actually doing anything useful. So it avoids deadlock, but generally you don't want to have, if you can avoid hold and wait, you've broken deadlock, but if you just avoid hold and wait, you can actually have this terrible condition called live lock. So that's something to be aware of. No preemption. So how do we avoid preemption? Any thoughts? Anyone? Aaron? We can let the philosophers duel with each other? Oh, steal chopsticks, sorry. Yeah, so we can let philosophers steal chopsticks. I mean, so one way to do this is, how do you decide the stealing? How do you want to do the stealing? So you can steal it, but then wouldn't everyone steal the right chopstick and then everyone steals the left chopstick? Jake, you wanted to add something? Oh, yeah, so you can index the actual, the requests. So whoever has the lowest identifier can get the request. So yeah, you can do it. You actually don't even need to have a total ordering for this one. So one way to break a cycle is you just have to remove one node from the cycle. So what if we had a queen philosopher? That is the biggest crown for the smallest head. But we have now a queen philosopher. When the queen wants to eat, we let her eat. So by introducing introduction of priority avoids no preemption. So as soon as you introduce any form of priority, like a queen philosopher, you have now avoided preemption. So what we've done is now we have all four conditions of deadlock. We have ways to avoid all four conditions of deadlock. And as we think about different problems, and a lot of the homework for this week is thinking about these types of situations. What condition can we avoid in a given problem's context to avoid deadlock happening in that problem? So we'll see that as part of homework 5 that is going to be out today, as well as MP4, where you'll get to use conditional variables and mutex locks. I'll be here after class if you have any questions. And if you're missing any of your previous handouts, like if you missed a day of class and want them to fill out for the videos. All the videos for the previous lectures are up. I have some extra handouts from all of the previous lectures. So I've got these if you need them. Otherwise, have an amazing weekend. Good luck finishing up MP3, and I'll see you guys on Tuesday.